Well, welcome to this little video recording in which we're going to revisit an old friend, the electric dipole. Should have first been introduced to this early in the study of electric fields, where we looked at the interesting properties of this dipole, which is made up of two charges, equal in magnitude and opposite in sign. And each of them had a unique property known as its electric dipole moment. It's actually a vector that describes one dipole and contrasts it with another dipole. So we indicate that with the letter P, and the letter P, kind of a strange symbol for electric dipole moment, I don't know why they use that, but it's equal to the amount of charge on one end of the pole times the separation between the two charges. So that's a really tiny little distance. It might be, picometers or femtometers, things like that. And it's not the net charge, because of course the net charge is going to be 0. And we have to indicate the direction, just as I did there on the picture. It's opposite the direction that the field would be associated with that dipole. Remember, these have these interesting curved fields around them, and the dipole moment vector points from the negative towards the positive, and I'll show you why that's helpful in just a second. Now, I'm not going to write that my description of the moment vector, but you just can see that on the figure. And you'll notice I arranged it so when I rotate this around, that P vector will rotate right along with it. So what we looked at before was how these things get torqued when we put them into an electric field. So let's just consider that the positive end of this wants to be pushed rightward when it's in that electric field that I've drawn, and the negative end wants to get pushed leftward, just due to all the charges that are actually creating that nice uniform electric field. So if we let it go, it would certainly want to rotate like that, and that is what we call its most stable position. Well, now what we're going to visit in this chapter with potential energy is when things fall into positions where they naturally want to be, we refer to that as being stable or at its lowest potential energy state. So let's look at how much potential energy is lost in that quarter of a rotation that this thing just underwent. You see, each charge is now closer to whatever charges were creating the field by a distance of half of their separation. See, they're just rotating through the middle. So the positive is closer to the right side by half of s, and the negative is closer to the left by that same amount. Be careful, because when I rotate this, notice the P starts to look like almost like a D. So how much potential energy was lost in that case? What we're going to do is describe the potential energy as, this is electric potential energy. First of all, it's the charge times the field times how far each one moved through that field parallel with it, which is half of s. So we'll put s over 2. Sorry for the sloppy writing there. But that's for each charge. We have two charges that are each getting in a lower potential energy state. So what that does is it basically doubles this thing, and we can just cancel out that 2. So as a system, the entire dipole is lower by an amount of Q times E times S. Or what we can write is just P times E, because QS is equal to P. And because it's lower, we can put a minus sign on it. All right, so the change was negative. Remember, lower potential energies are more stable, and that's why we're writing the negative. So in that rotation, quarter of a rotation, that's how much was lost. But what if we had rotated it the other way? This certainly is raising the potential energy, making it less stable. In other words, it doesn't really like to be there. So we call that an unstable equilibrium position, and it will have raised the potential energy by that same amount, P times E. So here's what some clever person came up with, probably some math person. They said, wait, we can summarize all of these potential energy changes by doing the following. Let's call this condition that it's in now, where it's perpendicular to the field, let's call that 0. 0 potential energy. Now that's not the lowest it'll ever have, because remember, when I rotate it, it's going to get lower. but it'll get lower this way by the same amount that it gets higher if I rotate it the other way. So what you'll see written usually is the potential energy compared to what you're seeing there when it's at its perpendicular spot can be written as negative P dotted with E. Now the dot product, remember, accounts for the direction between each of those vectors. The way in particular it's done, let me just write it this way, is you just take P times E, the magnitude of each, and multiply it by the cosine of the angle that those two vectors are making with each other. Right now they're making a 90-degree angle, so we would include the cosine of 90, and sure enough we get 0, which is what I had stated at the beginning. Everything is relative to this. But when we rotate it in the direction it naturally wants to go, cosine of 0 is just 1, and so we get a big negative number. But when we rotate it opposite, we would put in 180 for the angle, and we would get a negative 1, which cancels out the negative in the front, and we get the highest potential energy that we can. So rotating this around, again, this is all a result of that torque created by the electric field. All that does is it changes the potential energy from here we have 0, here we have the minimum, here we have 0 again, and here we have a maximum. So it kind of oscillates around in potential energy. If we let this thing freely spin, it would oscillate in potential and kinetic energies. So that's what we're doing now with these electric dipoles, describing their potential energy relative to 0 being completely perpendicular. So hopefully that's enough to describe maybe what you've read or gotten confused about. Any more questions, of course, you can follow up in your classroom with the teacher. Thanks for watching.